All right, class, we're going to get started. So today we have a bit of ground to cover. So we're going to start with the Poisson distribution, which we didn't get to in the lecture on Monday. And then we're going to go on to talk about sampling. So how we choose, how we choose a subpopulation in order to make a determination or make a statistically significant determination about some question that we're trying to address. And then I would also like at the end to go over quiz 2, right? So go problem by problem through quiz 2 and discuss really what I was looking for, what are the different approaches you could have used, what are the kinds of errors that I saw on quiz 2. So that's where we're headed today. Any questions before we get started? Okay. So last time we were talking about PDFs, probability density functions, and I guess just to review, when we're talking about a PDF, we're looking at what a PDF really shows us is the relative probability of one event happening relative to another. So if we have a normal distribution, so if we look here at the normal distribution, which we'll be returning to when we talk about sampling, we can see that the relative probability of having a value that's near the mean, in this case that'd be a z-score of 0, is the highest, right, in the normal distribution. You know, for example, we can see how much more likely we are to get a value near the mean than we are to get a value at one, in this case, one standard deviation away from the mean. We have to integrate in order to turn this into an actual probability, and this is something that I think I was maybe not clear on last time. In order to turn this into a probability, right, where we want to answer a question of what is the probability of a certain type of event happening, then we actually have to integrate this PDF, and then that will give us the probability of events falling within a certain range. So for example, here we're showing this PDF that is shaded in blue between plus or minus 2 standard deviations or z-scores from +2 to -2. The area of that shaded region is what tells us the probability of getting an event between -2 and +2 standard deviations. In this case, 95%, roughly. So, so that's why we also spent some time talking about the CDF, right? That cumulative density function, which is the integral of the PDF. Because most of the time when we're looking at the PDF and we want, again, to turn this into a probability, we're going to use the CDF in order to get there. Another question was, where did the pi go in our discussion from equation 5 to equation 7? Sorry, where did the sigma go? One way to think of it is that, I'll give you 2 ways to think of it. One way to think of where that went is, this is like the PDF of a process with 0 mean and standard deviation equal to 1. So if we have a process with 0 mean and standard deviation equal to 1, we plug those values in to our PDF, our full normal distribution PDF, then we recover exactly equation 7. Another way to think of it is that if you were to we know that one property of PDFs is that they have to be normalized, as in the area under the curve must be equal to 1, right? So we take the integral from -∞ to +∞, the area under that curve must be equal to 1. That sigma in the denominator in equation 5, in fact, that whole square root of 2 pi times sigma in the denominator of equation 5 is what's required in order to have a PDF with a integral equal to 1. So in order to satisfy that property of PDFs, that's the factor that needs to be there. And that's where, again, this square root of 2 pi comes from in the normalized form. Okay. So it's not exactly just plugging in the definition of Z into this PDF, but because we need that normalization factor in order to maintain that property of PDFs. All right, any follow-up questions on that before we jump into one more distribution? Okay. So today, as I said, we have one more distribution in this LO6 notes, and we're actually going to be introduced to another distribution in LO7, the T distribution. But when we have to talk about sampling first. All right, so the last distribution in these notes is Poisson distribution. This is another discrete distribution, right? So it has a PMF, probability mass function, instead of a PDF, probability density function. So in that sense, it's like the binomial distribution, but it describes a different type of event, right? So remember, one of the trickier things about all of these different distribution names and definitions is just keeping track of when to apply one versus the other. And so Poisson is a distribution that we use when we want to model the number of events that are occurring and we have a infinite sample. So if we think about the binomial distribution, that tells us about the number of events that occur within a finite sample, the number of cancer cases that we have within a block of 120 people. We use binomial distribution. But if we have an infinitely large or a sufficiently large sample that we're looking at, and we want to know about the number of events that are going to occur within this very, very large sample, then we use the Poisson distribution. So you can think of it almost as like a limiting case of the binomial distribution. Okay, so when the number of events that we're looking for, successes or failures within that number of events, when that number of events goes to infinity, we end up with Poisson. So it's often used in model counts that don't have an upper bound. So we're looking at number of defects in a semiconductor device. Right, we have semiconductors coming off some processing line here, or maybe up in Idaho, right, one of our semiconductor plants. We might use Poisson to model that kind of a process. A number of earthquakes within a given period of time. Poisson distribution also models the number of people that are arriving in, for example, to wait in line at a store, right? So we talked about using the exponential distribution would tell us something about the time between arrivals, right? So exponential distribution had to do with the time between arrivals. Here we have a distribution of the number of arrivals, let's say, per unit time. So equation 10, what we're showing here is we're going to essentially showing that we can get this, or what the Poisson distribution looks like. So it's going to be, we're defining it mathematically. So it's shows the probability of a specified number of events, like failures, arrivals in line, whatever it is, over the times the average probability that those events occur, at lambda, is defined here. One unique feature of the Poisson distribution is that it's both its mean and its, there should be standard deviation, are lambda. So it has equal mean and standard deviation. So it's a unique, very unique distribution. So as an example here, we can show, we can use it to approximate our results from that cancer problem. We, again, just remember that was, suppose we have 120 people living on your block. Last year, 6 of them were diagnosed with cancer, and you're wondering whether or not you should move. So using binomial distribution, right, which we derived in that lecture 1, we showed that the probability of having 6, any group of 6 people on your block with cancer, being diagnosed with cancer in a given year, was this 4.5 times 10 to the minus 5, right? That was the probability. But we can also do this using the Poisson distribution. So we're going to say that we're going to have n times some number lambda, which we have to find, cancer cases distributed into some number of boxes, like the number of blocks that we have. And the x would be like the number of items in a particular box. So in that case, we're going to have this expression for the probability of getting, in this case, we're going to have 6, or look for the probability of 6 cancer cases. We'll see that it can be approximated using the Poisson distribution. And this will be true as n goes to infinity. And n of 120 is starting to get relatively large. We'll put better bounds on what large means here. But we'll see what answer we get if we approximate this with Poisson. And what we end up with, so this code more or less defines the factors that go into our Poisson distribution as we described above, and then computes that Poisson distribution value for 6 cases. And what we end up with is probability of 6 cases on a particular block. We get 4.9 times 10 to the minus 5, which is relatively close, pretty close to 4.5 times 10 to the minus 5. Right. So our the number of events that we were looking at of 120. Right. So we had 100. We were considering number of cancer cases within a population of 120. This number was getting large enough that the Poisson distribution gets pretty close to binomial. The rules of thumb for the use of Poisson approximation of binomial is that our n should be greater than or equal to 20, and the probability of any given event should be less than about 0.05. So under those conditions, then the binomial distribution is pretty well approximated by Poisson. And if we look here, our probability, if you remember, probability of any individual being diagnosed with cancer in a given year was this 0.005. And so, it was 0.005, and our n was 120. So we're just on this boundary as far as the probability is concerned. So we can rewrite this in terms of in terms of a rate of time. So I mentioned we can use Poisson distribution to describe processes like arrivals of people in line over a specified amount of time. So that is well modeled by Poisson distribution. And so if we rewrite that, so lambda is the average number of items or average number of events that we would expect to see over many, many trials. And so if we know the time rate for an event to happen, then we can rewrite that lambda is r times t, where r is like the average rate, and t is the time period. And then our Poisson distribution for k events in interval t is given by this equation 12. And so this could be, again, number of people that are going to arrive in line in Trader Joe's on Sunday afternoon or something. Then if we know, time, the unit of time, let's say we're looking over a 10-minute interval, then we would look at what is the average rate. If we know the average rate of arrival of people in line, then we end up with, we can compute lambda, and then we could use this to find the probability of any other number of arrivals over a 10-minute time period. That make sense? A little bit of sense? Okay, getting a lot of blank looks, but no one, so is there something about this that is not tracking right now? Yeah, go ahead. Yeah. So let's say we're looking at because Poisson distribution is famously used for looking at arrival events for people, shoppers in line or something. It can be modeled by Poisson. So let's say that's our example, and we'll look at an example down here as well. But let's start with that as our example. Then and we're going to look at number of shoppers that arrive over a 10-minute time period, right? On average over a 10-minute time. In a specified 10-minute time period. All right, so we're going to stand there at Trader Joe's with a stopwatch and a clipboard. We're going to count number of people that arrive over some period of 10 minutes, right? In order to model this using Poisson, we would want to know after, let's say, over many such trials of 10 minutes, what's the average number of people that arrived? That would be our number lambda. So another way to think of how to compute that lambda would be like R So T in this case is 10 minutes because we're looking at it, we're watching this line over 10-minute time period. R would then be the average number of people per unit per minute that arrive in line. So if we know on average there are, 2 shoppers arriving in line per minute on a busy Sunday, then our lambda would be 2 shoppers per minute times 10 minutes would be 20 shoppers. That makes sense?
Was it in the cancer example?
So yeah, so in the cancer case, it's the average number of items that we expect to see. So yeah, so it would be n, the size of the block, times the probability that any given person has that cancer. So n times p is what gives us the average number of cases that we'd expect to see per block. And then that becomes our lambda. But yeah, that's a good question. Yeah, okay. All right, other questions? Okay. And so what we can see if we, in comparison to equation 10, is we've replaced our lambda basically just by RT, right? So where RT is just the rate, average rate times the time period over which we're watching these observations. So an example would be probability of getting 2 500-year floods occurring within the next 50 years. So, a 500-year flood, the original idea of what a 500-year flood is that it's a flood so severe that it should happen only on average about once in every 500 years. Typically based on older data, so maybe that's not as true anymore. But we can use Poisson distribution to estimate the probability of having 2 500-year floods happening within a period of 50 years. So our rate of having a 500-year flood is just 1 over 500, 0.002. So our rate here is 0.002. The average rate that we expect to see a 500-year flood occur per year. Our time period is 50 years, right? We want to know the probability of getting 2 500-year floods within a 50-year period. And our K, our number of events, is 2, right? So we're going to use Poisson distribution to find the probability of having 2 such events in a 50-year period. So RT, or the lambda that we plug into the Poisson distribution, is just that rate times the time, right? So it's 0.002 times 50. And we're plugging that into our definition of the Poisson distribution, and we're going to look at the output. What we see is that the probability of having 2 500-year floods in the next 50 years is 4.5 times 10 to the minus 3. So it's not 0, it's relatively low, but not completely 0, right? Like it is possible to have 2 500-year floods within a 50-year period. And we can use Poisson distribution to kind of understand what that means, okay? So one of the key concepts here, I guess one of the key things here is that when we say 500-year flood, it's a statistical or probabilistic estimate of or a statement about flood strength. And so we can use probability to understand what that really means over a given time period. So I just want to talk a little bit about the behavior of the Poisson distribution. And we're going to return to this in the next piece of lecture notes when we talk about, in general, what happens to distributions as the number of samples gets large. So we'll look at what the Poisson distribution looks like for different means or different mean number of events, or different lambdas. So this is a plot of our Poisson distribution for a lambda of 5, meaning an average number of events that we observe equal to 5. So we can see that 5 is just barely, I believe, the most probable. Should be just barely the most probable. Actually, no, it's not. It's looks like 4 is actually just barely the most probable. So the average here is 5, but this distribution is skewed. And so we end up with 4 being actually just slightly the most probable. But again, we have this distribution. It's asymmetric, tails out towards a larger number of events. But one feature that we can see here, and again, we're going to return to this as we move on into the next section, is that as we have more and more events that we that occur over our specified time period or within our number of observations, we can see that this distribution, first of all, it moves out to the right, and that makes sense because as lambda increases, as the average number of events that we expect to observe increases, then our probability distribution should move to the right. Okay. The other thing, though, that you may notice, like, what does this look like? Looks like a normal distribution. And there's a deep reason why this looks like the normal distribution that we're going to only scratch the surface of in the next set of lecture notes. But yeah, this does start to become the normal distribution. And as the number of events goes to infinity, as lambda goes to infinity, the Poisson distribution becomes the normal distribution. But we'll talk a little bit more about that on the next, in the next set of lecture notes. So we can do the same. We can apply the same concept to look at what's the probability of a specified number of blocks with a specified number of cancers. Again, we're going to be using the Poisson distribution. In this case, lambda, the number of the average number of events. If you remember, we found that the average number of blocks within the United States on which we would expect to see 6 cancer cases within a year, we found to be 109. So here we're going to use that as the average event frequency that we would see. And we're going to ask now, what's the probability of seeing 200? All right. So if we know that the average is 109, what's the probability of seeing 109 blocks with 6 cancers in a given year? What's the probability of seeing 200 blocks with 6 cancers in a given year? And so again, we can approximate this with Poisson, and we end up with 1.8 times 10 to the minus 15. So we see that it's relatively not terribly probable that we're going to see that many cancer cases, or that many blocks with 6 cancers. So again, to return to the cancer example, so if we see this, this would be evidence that you would want to look for carcinogens, that you may have some kind of a cancer cluster type event. All right, so one more example, it would be to look at an example of how many raisins we're going to expect to find within a slice of a loaf of bread. So the idea is that a baker is mixing dough for raisin bread such that there should be 200 raisins per loaf, right? So that's the average number of raisins that we'd expect to see per loaf. And then we're going to slice that loaf into 20 slices of equal size. How many raisins should we expect to find within each slice, right? We could do this with chocolate chips or something that people actually want to find within their bread, maybe. Maybe it's a better example. But so let's say how many raisins do we expect to find in each slice is the first part. And then once we know that, what is the probability of finding 5 or fewer raisins per slice, right? So you might be bummed if you were looking for 5 or more than 5 raisins within your slice. Or maybe you're happy, right, in that case. So what's the probability of either of those? So on average, so for part A, we have 200 total raisins per loaf. We have 20 slices, so we expect to see about 10 raisins per slice, right? So that's the first part. And so that means lambda is 10, right? So the average number of events that we expect to see is 10. And then we want to find the probability of finding 5 or fewer raisins per slice. And we're going to do this using the Poisson distribution. But the thing to note here is that we need to find the probability of 0, right? Plus the probability of 1, plus probability of 2, plus probability of 3, 4, and 5. Does that make sense? Right, because we said it's not just a probability of finding a slice with 5 raisins, it's a slice of finding a slice with 5 or fewer. Right? So we're going to add up those probabilities. And that's what's discussed, that's what's described right here. So this is the sum of, in this case, we're going to go from 0 to 5 of the Poisson distribution with our specified lambda of 10, and x is going to go from 0 to 5. Another way of thinking about this is that this is really just a cumulative density function. So this is the same idea as a cumulative density function that we discussed for a continuous probability distribution, where in the continuous realm, we were integrating from minus infinity to any specified value was the CDF at that specified value. So here, because we have a discrete probability distribution, we're actually just going to add up the probabilities, right? Addition or summation over a range is the discrete analog to integration over that range. And so what we're actually computing here is the CDF of a Poisson distributed process. But we can find it by taking the sum over all of those different events, again, 0 to 5 raisins per lobe. And so we can do this, in this case, we're showing we can do it in 2 different ways. So the first is just by recognizing that what we're actually looking for is the CDF of the Poisson distribution. And the CDF of the Poisson distribution is built in to our library. And so in this case, we find that the overall probability, cumulative probability is 0.067. Right, so just under 7%. We can also find it by, again, just taking the Poisson distribution and computing Poisson distribution at each one of those values from 0, 1, 2, 3, 4, and 5, and just adding them together. It's the same thing, and we get the same result. Okay. All right, any questions on this? So I do want to move on to the next set of lecture notes. There's another example in these lecture notes for your review, if you want to look at another example of Poisson. But I want to get on to lecture 7, so we have some time at the end to look at the quiz as well. Okay. All right. Okay. So lecture 7 is about sampling. So when we have some process that we want to know about, it can often be expensive to collect data, expensive or difficult to collect data. And so we're going to have to take a sample of that data, right, or a sample of the population and do our analysis on a sample of the population. But the way we do that sample, how big that sample is, and how big that sample is can have a big impact on our results and on what we can say statistically about the results of our experiment or of our sample. And so in this lecture, we're going to start thinking about how to sample some kind of a process using a little bit more intelligently using statistics. And then in the next lecture, we're going to start talking a little bit more detail about confidence intervals. Confidence intervals have come up already when we're talking about linear regressions, for example. But we're going to talk in a little bit more depth about confidence intervals in the next lecture, which will take off from some of these concepts about sampling. For example, we're going to start with population. We're going to look at weights within that population. So we're going to use data that we looked at in lecture 3 on data frames. And we're going to look at how so if we treat the data that's in this file, cdc.csv, for a number of individuals with, so if we treat that as our population, we're going to look at what happens to our estimates of the mean, standard deviation, and should be variance, I believe, for sample sizes. Oh, sorry. Mean, standard deviation, and standard deviation of the mean, which is something a little bit different that we'll explain in this lecture, for sample sizes of 10, 20, 40, and 80. So we're going to ask if we have this population, right, which is given in this file, and we're just going to take out 10 measurements from it. It's equivalent to asking 10 people how much they weigh from that population. What do we get for the average, and how well do we know what the average is? Right, if we go in and we ask that same uncomfortable question to 20 people, how much better is our estimate, right? Versus 40 versus 80. Okay. So again, we load the data into a pandas data frame, looking at the tail in this case, just to see what that data looks like, and we're going to be talking about the weight here. So our population here is going to be for everyone that had gender listed as male and whatever there was in the weight field. And then we're just going to take samples out here that are samples of 10, 20, 40, and 80 people from this list. And we're doing this actually using this function that's built in that allows us to that takes a random sample of this data. Okay. And then down here, this next section of code is just going to be outputting the mean, the standard deviation, and the standard deviation of the mean for each of those samples. And so what we can see, we have mean of 10, mean of 20, mean of 40, mean of 80, right? These are all different numbers, right, from those samples. Since these are all samples, they all have different standard deviations. And we'll come back to this in a second, but you can see that if I run this code again, right? So now I just reran this cell that's equivalent to taking another sample of 10, another sample of 20, another sample of 40, another sample of 80. So I rerun that code. And now if I come down here and I run this section, you see I get different results, right? So my mean, my standard deviation are changing. So I'm going to go up here, I'm going to do it again. And I come down to this section, run this section, you can see that they changed. Now I want you to pay attention to how much the mean of 80 changes as I do this. Probably written something to automate this, but so I'm going to run this. So I'm taking it, I just took a new sample, and now I'm running the next bit of code. And you see that the mean of 80, it went from 188 to 185. And do it again. Now it's 192. I'm going to do it again. Now it's 181, right? So it's changing by, so it's mostly around the high 180s or so. Now look at this mean of 10. Right now it's 197. It's coming from the same population. Let's run it. Now it's 183, 191, 180. So it's it's a bit lower than what we saw previously. 196, so quite a bit higher than what we had. 175, right? We just got a mean of 175. And note this mean of 80 was staying much more consistent. So the size of our sample, as you might expect, if we have a larger sample size, it's giving us a more consistent mean from essentially what I'm doing is running experiments, right? From experiment to experiment, I'm getting a more consistent mean when I have a larger sample. You see that in this? So when I took samples of size 10, I see a large variation or relatively large variation in the average weight that I computed, or a variation that was larger than what I saw when I measured 80 people, right? When I sampled 80 people at once. So these numbers were fluctuating more than these. And that's what's captured here. When we say standard deviation of the mean, so this is an estimate of how uncertain my result is for my population, for my sample size of 10. And this is my estimate of how uncertain my estimate of the mean is for a population sample size of 80. In general, this tends to decrease. Our uncertainty decreases as we increase the sample size. You can see that doesn't exactly follow here because there is uncertainty in this value, and we are using the sample statistics in order to compute this value. But you can see the general trend that in general we have less uncertainty in our understanding of what the mean is when we measure more people. Does that make sense? So there's some intuition there. If we want to know the average weight of a certain population, right, that's what we're looking at here. If I ask 80 people, I have a better understanding of the average than if I ask 10 people, right? And that's what's reflected here in the standard deviation of the mean. Yep. Standard deviation of the mean is also standard error of the mean. That's correct. And yeah, we will describe that just down below. Where have you encountered standard error? of the mean? I guess we talked, it's come up a little bit, but we haven't rigorously defined it. Okay. Yeah, so standard deviation of the mean is also sometimes described as standard error of the mean. Yeah. Was there a question? No, okay. Another way of thinking of this standard deviation of the mean or standard error of the mean is if I were to just repeat this experiment many times. In this case, I'm going to repeat the experiment 500 times, where I'm going to sample 80 people. I'm going to pull 80 people out of this population, ask for their weight, and compute the average. And then plot just all of those averages that I got, right? So I'm running this experiment where I'm polling 80 people. I'm running this experiment many, many times. And just looking at the distribution of average values that I compute from those samples of 80 people. This is the distribution that I got when I did that once, and we can do it again. Right, so I'm getting a distribution of averages for the weight within this population based on my sample size of 80. And if we look at this has a standard deviation of about 3 or 4 or so. And if I were to make this number smaller, so if I make this number smaller, what happens to the width of this distribution? So I want a show of hands. So does it decrease? Raise your hand. Does it stay the same? Raise your hand. Does it increase? Yeah, I want to see more hands. More people participating would be great. But anyway, it does increase, right? So if we decrease the sample size, then our uncertainty in the mean value from that sample is going to increase. And we should see this thing get wider. So let's check if that's actually true. Right, so we see that now we have values ranging from 160 all the way up to 230, and the center of the distribution has gotten quite a bit wider. We can run this again. And again, we see that's not a fluke, that in fact we do have a wider distribution here than we did when we had a sample size of 80. Okay. So again, kind of aligning with intuition, if we're trying to measure, in this case, the average weight within a population, the more people we ask, the better idea we have of what that average value is. And so the way we express this is that the standard deviation for the distribution of mean weights would be sigma over square root of n, right? So this is standard deviation of the sample mean. Remember, x bar is the sample mean, is sigma, the standard deviation of the population, divided by square root of n. Okay, and so this reflects that if n increases, then our standard deviation goes down, right? Our uncertainty in what that mean value goes down. So we ask more people, we get a better idea what the average is. A note here, a caveat, is that we don't usually know the population standard deviation, that's sigma. Normally we know the sample standard deviation, S, instead of sigma, and this is going to have some implications for the way that we actually compute this, but we'll talk a little bit more about that. So now we can start to look at the like how big should our sample be, right? So we can start to say something about how big our sample can be, should be. So let's say we have so just to summarize what we just discussed, if we're going to make n independent measurements, like 10 or 80 independent measurements of a population with a variance sigma squared or a standard deviation of sigma, and then what we're trying to do is calculate the mean of that property. So we're looking for the average weight of the population. Then the standard deviation of that mean is proportional to 1 over square root of n. All right, so that's what's encapsulated in the formula that we had previously. Right, which is shown here again. So the standard deviation of the sample mean is sigma over square root of n. So this means that a factor of 4 increase in n, so if we go from 10 to 40 people that we measure, or that we ask about their weight, this decreases the spread of our mean values by a factor of 2. So one thing that this is telling us is that we have kind of a case of diminishing returns, right? So as we ask a larger and larger population, our uncertainty in the average that we compute, the mean that we compute, goes down, but it goes down more and more slowly as we ask more and more people. This is kind of at the heart of this question of sampling and how big should your sample size be? Because there's probably going to be some kind of an optimum sample size where you're balancing the cost required to actually acquire the sample versus the additional information that you're going to get. So another thing, though, that we should keep in mind here is that the expected value of the average of the population average is going to be just mu. So put another way, if we're sampling people about their weight, and we're taking, let's say our sample that we're computing as X bar is from a sample of 80 people, right? We're asking 80 people about their weight. The expected value or the average value that we're going to see for the average weights within our sample is mu, is the average overall. Make sense? So the average of the averages is the average of the population. So another way is if we think of if we have a normal distribution like we would expect for heights or weights, the mu, the average of those values is going to be right smack in the middle, right? So the population average is going to be right smack in the middle of that. What this is telling us is that if we then make a measurement of 80 people within that population, we should expect that the average of our sample of 80 is somewhere near that, the average from the overall population. Does that make sense? A little bit more sense? Okay. It does get a little tricky when we're talking about averages of samples. Or another way of thinking of it, if I look at this plot here, so in this case, I was effectively running like a numerical experiment where I'm making 500 different samples of size 80 from this whole population. The average value of this distribution is, we should expect it to be very close to the sample mean. And even if I change this to 10, we should see that the average is still about the same, right? So the expected value of the average of our samples is equal to the average of the overall population. And that doesn't change as we change n. So in this case, we change the width of the distribution by reducing the number of people that we asked, but the expected value that we get is still the same, right? The center of this distribution is still the same. So I can take this out to 100, and we get a tighter distribution, but it's all right around the same average. So the question here is, what is the shape of this distribution that we're going to see? So if we have like the shape of the distribution of the sample means, right? So now this is, if we imagine that we're again taking we're doing many experiments where we sample a certain number of people, and we ask, what is the shape of this distribution? Or what shape do we expect for this distribution? We can start to get at this by saying that through something called the central limit theorem, which again, and we're going to look at some consequences of this down below. But the central limit theorem says that no matter the form of the parent distribution, so no matter what the PDF, the underlying PDF looks like, as we increase the number of samples that we're taking, then the distribution of whatever that, of the thing that we're looking at becomes approximately normal. So central limit theorem, in application to this specific example, tells us that what we should expect to see as the number of samples goes to infinity is a normal distribution. So we should get a normal distribution as the number of samples goes to infinity. And we will consider, for a rule of thumb, we're going to consider a sample large if we have at least 30 independent observations. So we'll say that if we have about at least 30 independent observations, then we can use the normal distribution in order to find the probability of getting a sample with any specified range of average values. But this idea of the central limit theorem, I'm just going to scroll down to the central limit theorem. The idea of the central limit theorem can apply to any distribution that we have. So we saw this in the Poisson example just at the end of the previous lecture notes. So if we looked at the Poisson distribution for the number of events increasing, we saw that we got increasingly a curve that just became increasingly bell-shaped, right? And in fact, it's actually tending to be exactly a normal distribution. It's not just something that looks like normal distribution, it's actually tending to the normal distribution as the number of events increases. And the same thing is actually true regardless of what the underlying distribution is. If we take many events with any specified distribution, and we look at the summation of those events as the thing that we're looking at the probability of, then no matter what the initial shape of the distribution, it tends to a normal distribution as we have infinitely many events. So this is called the central limit theorem, and it's why the normal distribution is so useful, right? So it tells us why the normal distribution is so useful, because if we have some process, which is the sum of a number of random events, or a large number of random events, then no matter what the underlying probability distribution of those random events, if we're looking at the sum of all of those things together, we're going to end up with a normal distribution. So this is why it's so ubiquitous, why normal distributions appear in things like height and weight and all kinds of other data. It's because of this idea encapsulated in the central limit theorem. So this is showing examples. So if we just take a uniform distribution, so we can think of that as being an approximation of what you would see if you had a die. So you can do the same thing with die rolls. So if you take a uniform distribution so you roll a dice one time, we know we have a probability of 1/6 that we get any given number to come up, right? But now if we ask, what does the probability distribution look like for 10 rolls or 20 rolls or 100 rolls? As we keep increasing that number of rolls and we're adding up the numbers that we see on each individual roll, what we end up with is a normal distribution. So we can start with something that's a uniform distribution, we end up normal. We start with exponential, log normal, any distribution you can dream up, we end up with a normal distribution at the end. So we can use that then to approximate what happens with our sampling process, right? If we have a large number of samples, we can look at. So we can do a similar kind of analysis for what happens with sample size if we have a discrete distribution. So we'll start with the binomial. So let's say we have a process that is approximated by binomial distribution. We had approximate proportion of successes would be P. So we're going to say P is the number of successes, average number of success. P hat is the number of successes within the sample divided by the sample size. So it might be 6 over 120. There were 6 cancer cases in a block of 120. We know that for the binomial distribution, the mean was NP, and the standard deviation was given by that square root of NP times 1 minus P. And so we can then find an estimation of the, so we're trying to say, like, if we make a sample of events, what is the average value that we expect to see within that sample? And it's just going to be the same as the average that we expect to see for any individual process within that sample. So it's just that x over n. And the standard deviation is going to be the standard deviation of the individual overlying process divided by square root of n. And again, what we would see is that for large sample size, the distribution of the sample averages is approximately normal. And here we're just giving some limits on what large means in this case for binomial. So I want to talk about the t distribution. So this next section here, this is the, I'll leave this for you to look at if interested, and maybe we'll have a homework question going through a piece of the derivation. But this is more or less showing us basically why we expect to see the sample standard deviation go as, the sample mean standard deviation go as 1 over square root of n. And what it comes back to is something that we're going to talk about from quiz 2 that we talked about in lecture 1, which is if we have, remember we wrote out an expression for the expected value of the sum of the linear sum of some random processes. And so we wrote out that expression. We also have an expression for what the variance is for the sum of some random processes. And so we can actually use those expressions, again, from lecture 1, to derive this result that the standard deviation of a sample average goes as 1 over square root of n. But in the interest of getting to this piece, which we need to set up our discussion on confidence intervals, we're going to talk about the t distribution. So, up above, I said that, or just previously, I said that if we have a large sample size, so in practice n greater than 30, then we can use the normal distribution to make up an estimate of the probability of seeing any given mean value or any range of mean values within a sample. But that requires that we have a large sample size, and it also requires that we know the sample standard deviation sigma, the population standard deviation sigma. We often don't have such a large sample size, but we still want to make some kind of an estimate of what's the probability of getting a given value from our experiment. And we generally don't know the population standard deviation. If we knew the population standard deviation, we wouldn't have to be doing the sampling in the first place, generally. So in place of that, we're going to be using what's called the t distribution, which basically just allows us to make statements about the sample mean and how probable it is to get a given value of the sample mean. And so in the t distribution, we're going to be using, instead of sigma, we're using the sample standard deviation. So again, this is the standard deviation with this 1 degree of freedom. So it's n minus 1 instead of n. And instead of using the z statistic, where you're going to use, which we used in the description of the normal distribution, we're going to use the t statistic, which is more or less the same, but now we're replacing sigma by s. And notice that in this case, the denominator here is the standard deviation of the means, or the standard error of the means. So this random variable t here is distributed according to what's called the t distribution. And we're not going to derive the t distribution here, but we'll show what it looks like. So again, the standard deviation of the mean, or our estimate of the standard deviation of the mean, is s over square root of n, sometimes written as standard error, right, or SE. And so we can rewrite this t statistic as x minus mu over SE, or x bar minus mu over SE. So we can look at this t distribution based on the number of degrees of freedom. So now when we're talking about degrees of freedom in the context of a t distribution, that the degrees of freedom here are going to be n, number of measurements in our sample -1, so n -1. And when we plot our t-distribution for varying numbers of degrees of freedom, we can see that with a low number of degrees of freedom, a small number of samples, we get this blue curve, and it tends towards the normal distribution. So this t-distribution is more spread out than the normal distribution, but it tends towards the normal distribution as our sample size becomes larger. So it approaches the normal distribution, which was the result of our central limit theorem. Okay. So I think the next piece of this is going to be the use of the t-distribution, which is really going to dovetail into our confidence interval discussion on which we're going to have on Monday of next week. I am going to push that off until Monday of next week so we have a chance to talk about the quiz. Okay. Also because we're getting to an hour of lecture time, and I feel like that's about the max that we can do in a given day. Any questions on what we have so far on sampling? So we introduced the t-distribution, and we talked a bit about the shape of the t-distribution. We'll look a little bit at the use of t-distribution on Monday. But any questions on this before we talk about the quiz? Okay. All right. So what we'll do now is maybe we'll give it just 5 minutes or so before we start talking about the quiz. We'll break here. Anybody who doesn't want to stick around for discussion of the quiz, now's your time. And in about 5 minutes or so, or depending on how things are quieting down in here, we'll start talking about the quiz. Okay.